So this is today's presentation agenda. Today we are going to discuss about the de-risking control model development for production development of production solutions, and whatever the control or validation methodology we are going to use it. Okay, so generally we used to define control validation methodology in each and every stage of productions they are going to discuss. Then as a RCP provider, right, we are going to discuss how we are going to convert our mathematical simulating model to hardware implementation, single click transmission. Then what are the mission critical applications we have already proven as a reliable solutions, RCP. Okay. Then our ingeniously developed product called rapid control driving solutions that we are going to discuss, and followed by some hardware demonstrations and then Q&A sessions. Okay. 1 minute. Yeah, so I'll move on to the next slide. Okay. So in modern control systems are becoming more complex, right? So it's demand higher performance, stricter regulations, and tighter hardware and software integration. Okay. So at the same time, development timelines also shrinking and leave almost no room for late stage surprises. So when control models issues are discovered in late, okay, during integration or production stage, the impact is significant. Okay, it often leads to costly redesign across hardware and software, which triggered to extended validation cycles. That at then it is going to affect to the production delays. Okay, and that increase product risk and project cost also. Okay, the most effective way to prevent this is through early validation. So how we are going to validate early? By using the rapid control prototyping, we can validate it early. So we can identify the design flaws or design issues when they are still easy and inexpensive to fix. Okay. So this allows proactive integration testing, because user can directly integrate the hardware and directly test the control flows. Okay, and it improves control robustness because we are going to test iterative test for a hardware plan or for control logic or for ECU units. Okay, and it replaces unstructured trial and error debugging with a systematic validation approach. Okay, and the impact is also significant, as we can see it over here. It improves faster development cycle, reduce integration risk, predictable production, and lower overall project cost. In short, if I want to say about de-risking control model development, right? So it is not about more testing. It is about testing at the right stage. It enables faster and more reliable production outcome. Okay. Now let's see. Now let's look at the different validation strategies. Okay, used across the development life cycles. Okay. So now RCP, rapid control prototyping, HIL, hardware in loop, and SIL, software in loop. Okay. So each those are the three key validation approaches. Okay, are going to use for development life cycles. Each serves a specific role in control development and validation. Choosing the right approach at the right stage is critical for development efficiency as well as overall confidence. If we use them incorrectly or skip any step, it either slow down our development, okay, or introduce late stage risk. Okay. So in the next slide, I will going to break down when and why to use which validation strategies, and how each one of them is going to contribute to a de-risk path to production. Moving on to the next slide. Okay. So those are the different validation strategies. Okay. So I'll start with the software in loop. Okay. So software in loop generally used in the early control algorithm development and functional validation stage, where both control logic and plant are software models, okay, and simulated in simulation environment. This allows us very fast iterations and without any hardware dependency, because initial stage we have to develop our control logic and we have to simulate iteratively to verify or to validate our control logic rapidly. Okay, so SIL is generally ideal for validating control loop, mathematical equation, and overall algorithm behavior. However, this software in loop does not capture real-time constants or hardware effects, so it is not sufficient alone by itself for production readiness. The next is rapid control prototyping, which bridges the gap between simulations and real-time hardware. In rapid control prototyping, the control algorithm runs on real-time controller or real-time target hardware while interacting with the real IOs like real sensors, real actuators, or a real plant. Okay, so this stage is critical because it reveals with real issues like hardware timing, their iOS behavior, integration challenges, and this stage we are going to do before issue electronic control unit availability. Okay. So RCP significantly reduce the risk by validating the control performance under realistic conditions. Okay. Finally, we'll move on to hardware in loop or HIL system. So HIL is typically used before production, where the actual embedded controller is going to test against real-time simulated plant. Why real-time simulated plant? Because HIL allows safe testing. Yes. Yeah. So HIL allows safe testing of edge case and fault conditions, failure scenarios that are difficult as well as unsafe to test on real hardware. Those scenarios, if you want to test it on, you want to test those scenarios in issue unit, we have to use hardware in loop systems. Okay. So this stage is essential for final validations, regulatory compliances, and safety certifications. Okay. So now, when these strategies are used together in right sequence, these strategies drastically reduce the development risk and ensure a smooth and predictable transition to production. Now, in the production stages, the first step it will come into software in loop, where algorithm design and functionalities is going to test, means where control logics are designed, functionalities of the logic and is validated in simulation environment. Okay, fine. Now the choosing the right validation strategy, okay, and in the right phases is crucial. Okay. Now, what is the right validation strategy? So first stage is software in loop or SIL, okay, where algorithm is going to develop and functionalities are going to validate in simulations. Once the first phase is done, then we'll move on to the second phase, like called RCP, rapid control prototyping, where the control logic is going to validate against the real hardware. Okay, and before controller unit availability. Okay, by using some rapid control prototyping blocks or real-time controller. Okay. Once that RCP validation is done, next stage is hardware in loop systems. Okay, where the final controller is tested against a high fidelity virtual plant. Okay, and this enables safe edge case testing and fault testings. Okay, those are very difficult or unsafe, we can say, when it comes to test in real scenario. Once the HL testings are done, by that time we reach to productions, the control system has been validated at every levels. Okay, ensuring confident development, deployment, and minimum risk. Yeah. Now, see the seamless transitions from model to hardware deployment. Okay. So one of the biggest challenges in control development isn't the designing the control logic. It is about how we are going to move from our control algorithm simulation to real hardware implementation. Okay. So this slide shows how rapid control prototyping removes the barrier. In traditional ways, once the control logic is validated, okay, in simulations, the real work began. How engineers had to manually rewrite the control logic, either in C code or C++ code, integrate low-level drivers, and then spend weeks on debugging to make sure the behavior of the hardware matches with the simulations. Okay, this is traditional flows. The process is slow, error prone, and made it very difficult to iterate to a complex algorithm. Okay. Now, where the RCP come into picture, with modern RCP, rapid control prototyping, the same simulink model is used in simulations is automatically converted into real-time executable code. Okay. There is no hand coding or no manual coding is required, no manual driver integration is required, and complete traceability from model to hardware. Okay, without control. This allows engineers to deploy, test, tune, and iterate in real times. Okay, this is a standard flow RCP used. Okay, fine. Now let's see, okay, how RCP is going to help seamless transition from one-click transmission from MATLAB Simulink to real hardware. So everything start in Simulink, okay, where control engineers design the control logics or control algorithm using standard block sets or built-in control libraries. Okay. So at this stage, the focus is purely on control performance, okay, and functionalities. And here, as I told you, here everything we are doing on simulation environment, right? So we are not going to consider the harder constant and low level implementation details. Once model is developed in Simulink, then next step is autocode generations. Okay, with autocode generation, by single click only, we are going to generate the optimized C code. Okay, by using a MATLAB Simulink embedded coder. These compilers automatically takes care of real-time constant, scheduling, and IO mapping. Okay, and eliminating the need of manual coding and driver integrations. Once the automatic code is generated, the next step is deploy to hardware or deploy to real-time controller. The controller executes the model or by taking the generated code, the controller executes the model with deterministic timing, ensuring predictable and reliable timing behavior. Once it is deployed, then we can monitor the real-time performance, like all the parameters we can monitor in real time. We can tune all the parameters, whatever the input variables, right? We can tune all the parameters, we can tune the control loops, okay, and immediately we can see the response. Okay, and we can do iterative test also, okay, by using this flow. Okay. Any changes we are making in the model, okay, can be redeployed in seconds. It won't take not hours or days. So instead of slow manual code generations, right, these flows really help us to do iterative test, okay, and it is a reliable and traceability from hardware to sorry, from simulation to hardware implementations. Okay. So in the right hand side, the image is represented here. You can see it over here. The control logic, right? From the control logic, we can directly generate the code or implementable code. That code we are going to load to the real-time controller. Okay. And then we are making the real planned connections. Okay. And by connecting the PC, we are going to monitor all the iOS interface or all the parameters we can visualize, all the control loops we can tune it in real time. Yeah. Okay, so now next is mission critical systems, where control failure is simply not an option. Okay, so wherever it's power electronics, motor control drive, or safety critical applications, right? In this system, even small issues, okay, like timing error, jitter, or unstable control loops can lead to performance loss, okay, or hardware damages. This is where rapid control prototyping plays a key role, and it provides a proven and reliable validation approaches. Okay. Now we'll see what are the proven applications, okay, that we have already tested. Now starting with the multi-level inverters, where control complexity is very high, we have validated complex modulation strategies, voltage balancing algorithm for high voltage DCAC systems, ensuring the stable operations, okay, even under dynamic load, as well as different switching conditions. Now DC-DC converters. In DC-DC converter, especially for renewable energy or EV charging applications, control loops are operated at sub-microsecond time range. So RCP enables real-time validations of buck converters, boost converters, bidirectional DC-DC converters, ensuring fast transient response, okay, and a stable power delivery. Now for the motor control, we have validated advanced strategies like field-oriented control, direct torque control, or sensorless control. This applies to PMSA motors, induction motors, BLDC motors, SRM motors drive. Okay. Those are generally used in automotive or aerospace applications. Okay, so where precision and reliability are critical. Okay. So finally, in high frequency control applications, we validate switching frequencies ranges from 100 of kilohertz to megahertz. Okay. For like resonance converters or advanced power corrections topology applications. Okay. So now across all the domains, the common requirement is deterministic real-time behavior, okay, and safe validations. Okay. So that's what makes a RCP a proven solutions for a complex mission critical control systems. Yeah. Okay. So now I'll move on to our indigenously developed rapid control prototyping solutions called True Control. Okay. So it's a advanced real-time controller. Okay. It supports powerful model-based design, okay, and fully featured debugging environment in real time. Okay, so I am going to discuss about each and every point in the upcoming slide. Okay, so it's a universal controller. Okay. One controller can be applicable for many applications. All power electronics applications, this controller can be applicable. Yeah. Now come to the technical specification of the controller. So True Control is based on Xilinx Zine system on chip device. Okay. In system of chip device, it generally constant it contain FPGA as well as ARM processors. So FPGA here we are using for IO interfacing, means all the hardware IOs are going to interface to FPGA. Okay. And all the protections logic is going to independently run on FPGA. Okay. And here we are using dual for ARM processors. Okay, so in ARM processors, we are going to do the management. One we are using for management, and other one we are using for control logic executions. Okay, so here we can execute the control logic with faster sample time up to 10 microseconds. Okay, and a PWM switching frequency generation up to 1 megahertz. Okay, with 10 nanosecond resolutions. Now, those hardware IOs are high-speed IOs interface with FPGA of the controller. Okay, so those IOs are generally embedded. So I'll start with our controllers. Okay, so as a RCP product or rapid control programming solutions, we have developed our indigenously developed rapid control programming solutions called True Control. Okay, so it's a universal solutions for power electronics. So by using this controller, user can do multiple all power electronics applications. User can do it some power electronics application doesn't like DC converter applications, grid connected applications, then power quality applications. Okay, those applications user can do. It supports powerful model-based design. Okay, and fully featured debugging environment in real time. Okay. So all these points I'm going to discuss in the upcoming slide. Now, True Control. So it is based on Xilinx Zine system on chip device. Okay. So in system on chip device, it contains FPGA as well as ARM processors. Okay. So FPGA we are using for IO interfacing because all the IOs we want high speed IOs interface. Okay, and the protections we are running on FPGA, so it is independently from the control logic. Okay. And the ARM we are using dual core Cortex A9 ARM processors. Okay, so in the ARM processors we are going to execute the control logic. Okay. The faster sample time that we can run up to 10 microseconds. Okay. And the PWM switching frequency we can generate up to 1 megahertz with 10 nanosecond resolutions. Now, when we are talking about high-speed IOs, right? Those high-speed IOs are embedded voltage and current sensors. Okay. Then high-speed PWMs. Now, whenever you are going to test any real hardware, right? The main thing is like protections. Okay, because we are going to develop our control logic from simulating to directly on hardware, right? So we don't know the hardware constraints. Okay, if some loop is not working or some loop is going in unstable region, right? This can damage this can give the we can say difficult or unusual output. Okay, that can damage to real hardware. Okay. So in True Controller, we are providing inbuilt protections. Okay, those protections are interface in FPGA only. Okay, so whenever any protections will trigger, okay, those protections are generally over voltage over current protections, under voltage under current protections. Okay, and PWM short circuit protections. Okay, so whenever any fault will trigger, the control will automatically detect the fault and it will turn off the controller. Okay, turn off the controller in the sense it will turn off the PWM from the controller so that your converters will be safe. Okay, and from the controller also you will get one buzzer sound, and from the software also you will get a software indication. It will indicate that some fault will happen. It may be voltage fault, or it may be PWM fault. Okay, so in the right hand side also you can see it. Okay, so user can give different threshold value. Okay, at what level they can generate, they want the protection stuff, right? So once the actual value is crossing the threshold value, that time the fault will be enabled. Okay, and the PW all the PWs will going to turn off. Okay, okay. Now coming to the iOS specification, those controllers are content with all the high-speed iOS. Okay, those iOS are embedded voltage and current sensors. Okay, those current sensors are voltage sensors are range of plus minus 1000 volt. It can measure both DC and AC. Okay, and the bandwidth of the controller is 256 kilohertz. Okay, and all are sample data 200 kbps sample rates per channel sensors, voltage sensors we are using. Then current sensors also maximum current sensors we can integrate to the controller. Is
Your voice is breaking,
number
Saikat.
of current sensors and analog input channel. If user wants to implement even a 10 volt ADC, by using those ADC ports, user can integrate their own sensors or actuator.
Hello. Can we
Yeah.
just go to 15th slide?
So our rapid control prototyping solutions, true control, right? It is based on Xilinx Zing system on chip device. Okay. So in SoC, it contains FPGA as well as ARM processors. Okay. So FPGA we are using for I/O interfacing because we want all the iOS to be high speed iOS. Okay, and all those embedded sensors we want independent protections also. Okay, because of that only we are interfacing all the iOS to FPGA. Okay, and for control logic complexity issue, we are using the ARM processors. Okay, for developing the for executing the control logics. Okay, the faster control logic or sample time it can go up to 10 microseconds. Okay, or you can say loop time. And the PWM switching frequency, those also we are using FPGA to generate the PWM switching frequency. Okay. So up to 1 megahertz switching frequency you can generate from our controller. Okay, with 10 nanosecond resolutions. Okay. Now those IOs we are talking about high speed IOs. Those IOs are generally embedded voltage and current sensor. Okay. Then high speed analog input and analog output channels. Okay, and ready to use PWM ports means if you want to run any converters, right, we can generate directly 5 volt PWM pulses from our controller or 15 volt PWM pulses from our controller. Okay, that pulses directly I can give it to any converters. Then other communications channels also are available. Okay, those communications channels are generally canned communications protocols we are providing. Okay, then RS-232 and RS-484. Okay, those communication channels are providing along with the controller. Yeah. Then we are using our standard MATLAB Simulink model-based design, okay, as a RCP solutions. User no need to worry about manual coding. Directly by single click only, user can generate the code. Okay, user can generate the executable code or binary code from the control logic. That same control logic user can load it to the controller, okay, and do the iterative test on hardware. Okay, while monitoring all the values, all the output parameters, then tuning the loops. Okay, all the loops also user can tune in real time. Okay, all the transient response or sudden response user can visualize by using our software. Okay. Then some data logging options also available. Okay. those things are available. So I'm going to discuss in the next upcoming slide how our software looks like and how those parameters and all, how we are going to visualize and monitor. Yeah. Now, True Control comes with inherent protections, okay, protections features, okay. So those protection features, as I told you, it is run independent of FPGA logic only, okay. So those protections are generally over voltage, over current, and under voltage, under current, as well as PWM short circuit protection. Okay. So if any, let's say if and user can okay, in any fault will happen, okay, at the PWM end. For that, before both PWM both top PWM and low PWM is simultaneously turn on, so it can damage our converters. Okay, that time the controller is automatically detect the PWM level, okay, and it will turn off the PWMs. Okay, and from the controller you will get a buzzer sound. It will indicate some fault will happen, and the software also you will get a software indications that will indicate you like which particular fault will happen. Either it is voltage sensor fault or it is like some PWM fault. Okay, it will indicate from in software. Yeah. So now those are the IO specification of our controller. Okay. Those IOs are generally voltage and current sensors. Okay. Then okay, then analog input channels also we are providing plus minus 10 volt analog input channel. Okay. All sensors are sampled at 200 kbps per channel sample rate. Okay. Then PWM channels, we are providing ready to use PWM channels along with supply as well, because some of the converters require supply also for the same voltage level of PWM. Okay. We are providing that also. Then digital input and digital outputs also are there. So 16 digital input and 16 digital outputs are there. In input, it is 3.3 or 5 volt tolerance, okay, and output is 3.3 volt. Then encoder and some relay interface also are providing. So encoder generally used for any drive applications, okay, where we want to estimate the rotor positions of the motor, okay, by using some Hall sensors or some encoders, okay. So that's why we are providing encoder interface also. And some relay interface also are providing if user wants to use it for some external protections of hardware by connecting to a external contactor or circuit breaker, that relay user can use it. Yeah. So this is the controller overview. Okay. So in the front, user can see it over here. All the ready to use PWM ports are available. So those are the ready to use PWM ports. Okay, both PWM level are 5 volt or 15 volt. Then the digital input and digital outputs are there. 16 digital input and 16 digital output pins are there. Okay. Then all the communications protocols also available. Those are the CAN communication protocols, RS-232 and RS-485. Okay. Then in the top you can see all the ADC channels are mounted. Okay. In the front you can see 8 DAC channels also there. Okay. And the back side all the currents and voltage sensors are mounted over here. And we have given one Ethernet port over here. By connecting your controller to your PC, okay, by using our software, user can execute the control logic, okay, and visualize all the parameters. Okay. Now for developing control logics, we are providing our built-in library. Okay, so those libraries are content all the soft ports that require for hardware interfacing. Okay. Those IOs are voltage sensors, current sensors, analog input, analog output ports, digital input, digital output ports, and iReg. So generally, we are providing if any parameters user wants to change it in real time, user can use on iReg options. Okay, so those parameters will be variable. So and user can, while running the control or executing the control logic or control loop, user can change the parameters. Okay, and probe also we are providing any signals of control logic. If user wants to visualize, user can use this, connect this probe, and this probe will help users to move on to the real time while running the real time execution. Right, these signals can be visible in our software. So let's see the control example model. Okay, how we are doing the executions and then the development. Here we are running one, let's say, motor control. Okay, so here the control logic of the motor, either field oriented control or DTC control. The control logic is going to will be inside one subsystems. Okay, and the simulated plant, right, is going to be one more subsystem or here. Okay. Now by connecting our IOs, we are interfacing like which ports, which parameters we are going to change it, and which parameters we are going to get the outputs. Okay. Those IO interfacing you have to do it. Once the IO interfacing is done, by using this blue color icon block, right, by single click only, we are going to generate the executable code for this control logic. Okay. Once the executable code is done, now from this that code only we are going to execute to the controller. Okay. Now we are providing our web suite real-time signal subtracting firmware. Okay. By using this software, user can tune parameters, user can visualize parameters, user can do measurement as well. Okay, let's say volt power measurement. Okay, then energy measurement. Okay, those measurement user can do it. Then data logging options also we're providing. Okay, user can log the data in any defined sample rates. Okay, for post data analysis. Then the customizable dashboard options also we're providing. Depending on different type of application, right? User can fully customize the dashboard. Okay, based on his requirement. Okay. Yeah. So here our dashboard or GUI this looks like. Okay. So what about the input in our control logic? What about the input parameters user wants to vary or tune in real time, right? Those input parameters, those inputs are coming to the input sections. Okay, and those input values user can change it in real time. Okay, and the user can see the signal performance or signal behavior. Okay, or transient behavior in real time while executing the control logic. Okay. Now, and what are the parameters user can see it over here? Those will come to this output section. Okay. By using this time plot, user can visualize the signals with respect to time. Okay. So in one time plot, user can maximum plot 8 number of signals. Okay. So let's say in this plot, we have plotted 3 voltage signals. Okay. VA, VB, VC, and we have visualized how the grid voltages, actual grid voltage is coming. Okay. And then if some control logics are implemented, we are checking the phase lock loop of the our control logic. Okay. So it's a normal applications we are running grid connected solar applications. Okay. So they are we are injecting the power from the solar to grid. Okay, and we are doing the real time executions by using the controller. Yeah. Now, when it comes to time plot, right? So we are providing instantaneous time plot. In this time plot, you can see it there multiple signals I can drag and drop. Okay, and I can zoom the signals. I can see the transient response of the signals. Okay, and on top of that, I user can save the figure as well as data in CSV file. Okay. Then general plot also you are providing. Okay, if user wants to do signal versus signals plotting, right? So user by using this our general plot, user can do the signal versus signal plotting. Okay. Now come to FFT panel. Okay. So we are providing FFT panel over here. If user wants to do the FFT analysis of any signals, okay. So by simply drag and drop that signal to this y-axis, we can see the fundamental frequency, fundamental component. Then all the frequency component contribute to this signals. Okay. And in the report sections also, we can see all the harmonic contribution for the different frequency level. Okay. Up to 50th order harmonies, we can visualize it over here. Yeah. Now come to power panel. So in this control, we are providing voltage and current sensors, right? So for that only, we are using the power panel options also. By using this power configuration, right, user can make their own power panel. Okay. So in this power panel, user can see the active power, reactive power, apparent power, and power factor. So these power panels is going to help when user is working in a grid connected application or power quality applications. Okay, or any motor applications also, you can see the how much motor is consuming active power or reactive power. Those things we can see. Then power analyzer also you are providing. Okay, by using this power analyzer, user can see the fundamental frequency, fundamental component of active and reactive powers. Okay, so then DC fundamental harmonics measurement also available with it, okay, with RMS, peak, angle, and power factor corrections. Yeah. Then energy panel also we are providing. And this energy data, right? User can log it in different time interval also. If let's say if we are running the one system for entire day, right? How much energy I have sent from the system, that also, if user want to do the data logging, that data logging options also available for energy. Okay. Now data logging of any high speed signals, okay, so that also available. So here you can see by selecting the signal rate, right, by that also user can select it, okay, and then for how much duration user to capture data, and how many we can say how many signals user want to capture data. Once user all select all those things, right, then user will click on capture probe, right, it will capture the data depending on the specific time interval, and those data will come to you in the form of CSV files. Now, as a R&D solutions for true controller, we have given different drive applications. Okay, so where we are running PMSM motors, okay, both field-oriented control and sensor-less control. Then BLDC motors. Okay, and then we have induction motor drive as well. Okay, then SRM motor with sensor. Okay, then DC motor drive, then EV emulator platform also here available. So we are running our EV motors, okay, by using our controller and by using the load emulator setup. Okay, we are generating the power, or we are testing the EV motor in 4 quadrant operations, and we are testing the motor performance, motor temperature, battery performance, everything we are testing it by using our platform. So in renewables and grid connected applications also, we are having many applications. Okay, in grid connected applications, we are having sun reactive power filter applications, then dynamic voltage restorer.
Right now, you are mentioning like for BLDC motor, have you implemented anything and you have seen that measurements is coming? And if it is like implementation on which type of controller, like there are like different techniques of BLDC motor commutation is there. Hall sensor based, like a sinusoidal FOC based. What kind of
Hmm.
thing you have done, and
Uh,
those things can we know, sir?
okay, so in BLDC motor, generally whatever the BLDC motor we are getting it nowadays, we all are coming with Hall sensors.
Hmm.
Okay, now based on the Hall sensor, we are estimating the rotor positions. Okay,
Hmm.
we are developing the commutation table. Okay, and we are running the motor in trapezoidal.
Okay.
Okay. And if it is PMSM motor, nowadays PMSM motors are coming. Some motors are coming with resolvers. Okay. Some motors are
Hmm.
coming with encoder, only encoder, and some motors are coming with Hall sensors. Okay. So if it is a resolver, it will give directly sine and cos signals, right? From the sine and cos signals, I'll directly get the theta. Okay. That
Hmm.
theta I can use for our Clark and Park transformations.
Hmm.
When it comes to encoder, we'll get only encoder pulse, right? From there, you have to generate the theta, right?
Correct.
From that theta again, you have to convert into that sine and cos required for the Clark and Park transformation.
Mechanical angle to electrical angle, we have to convert it.
Yes, yes. And if it is coming with Hall sensors, okay, then we are using Hall sensor only for trapezoidal control. Okay, trapezoidal excitation means two-phase excitations.
Hmm.
Uh, we are taking the Hall positions based on the rotor, and we are estimating the particular which phase you need to excite to get the to make the rotor to rotate or to get the maximum torque of the motor. Okay, so
Hmm.
based on that, we are getting it. Now, when it comes to FOC by using Hall sensor, right? We are using Hall sensor as well as encoder to get the theta.
Hmm.
From there, we are getting the theta, and we are converting into Clark and Park transformation, and we are doing the field oriented control.
Okay.
So
So
in
my
yeah,
yeah, my point is like, have you implemented these are all things using your whatever you are telling like tool? Because I have tried a multiple time using motor controller block set,
okay,
MATLAB is having,
uh,
and there we have seen like so many issues.
yeah.
And finally, we
So
have to implement like manually based. So
okay,
you are
okay,
telling like some tool is there. There you are seeing like this clocks and boxes transformation. Also, we can see these are all things you have told. No, that's why
okay.
I'm
So in the
specifically have
demonstration,
did you implemented like that?
okay, sir. In the demonstration part, okay, I'll show you the
Hmm.
MATLAB models, okay, and I'll show
Okay.
you how we are getting the code from it, and we are running the motors. As of now,
Mhm.
I am having the PMSM motor with encoder, okay, and hold
Okay.
positions. Okay. So while I'm going to execute, I'm going to run the motor, and I'll show you how we are doing the field oriented control.
There, did you kept like this dynamic loads only, or how did you consider
It is
payload per motor?
the motor is not, as of now, not coupled with any mechanical load or any dynamic load. Okay. Now it is we are rotating the motor only. But for some
Okay.
applications, we have already delivered with mechanical loading as well as electrical loading.
To
Okay.
answer your question, it is already being done and delivered, sir. And if
Okay.
if you wish, we can also come down to your place and demonstrate as how it behaves and all these things. That also can be done. We are not very far. We can always come down and show also, sir.
Yeah. It is much needed, sir. Thank you, sir.
Sure. Sir. Thank you so much. Yeah. Go ahead.
If anyone has any questions, sir.
Yeah. Does anybody so far any questions? You can proceed.
So in the hardware demonstration, right, I am going to run a PMSA motor drive by using field-oriented control. So this is the system architecture. How I'm going to run the PMSA motor. So this is hardware architecture, sir. We are going to present. We are going to demonstrate the PMSA motor drive by using field-oriented control. So here we are using the for DC bus, right? We are using AC grid and the rectifier module to maintain the DC bus voltage. Okay. And from the DC bus, we are measuring all the voltage of the DC bus and all the voltage of the motor terminals. Okay. And we are using standard IGBT based converter. Okay. To implement the to run the motors. Okay. And all the sensing, right? All the sensing and all we are doing by using this by using our controller. Okay, and the pulses for the control converter that we are giving from this controller. Okay, and we are connecting on Ethernet. We are establishing on Ethernet communication between the controller and the PC. Okay, and we are going to visualize all those things. Okay, so before moving on to the hardware, right? I'm going to show you the quick overview of MATLAB. Okay, how we are going to do all those things. Okay, I hope my MATLAB screen is visible, right, sir? So this is the softcodes or IO library toolbox we are providing along with the controller. Okay. So this will sit on the top of your control logics. Okay, those softcodes are directly related to your hardware ports. Okay. So if you want to use any hardware ports on the controller, you have to use this IO block to indicate or to tell your control logic like these ports I am going to use it. Okay. So those ports are generally voltage and current sensors block, PWM blocks and all. Okay. So okay, so this is in this subsystems my control logic is there. Okay, and outside the control logic I have connected so many blocks. Okay, now those blue color icon blocks are our development blocks. Okay, now if you can see it over here, we am using IRH blocks, right? Those IROs are generally we are using to make this input as a variable. Okay, those variables or values I want to change it in real time. Okay, for that only I'm using this IRS. Okay, and for measuring the motor current and motor voltage, I am using the current sensors, current sensor 1, and current sensor 2, and current sensor 3 for measuring all the motor current. And for voltage sensor measurement, I'm using all three voltage sensor 1 and voltage sensor 3. Okay, now for visualizing those signals, voltage signals or current signals, I'm using probe over here, so that directly in our software we can visualize those signals. Okay. Now, for getting the motor speed, right, we are using encoder interface. Okay, so inside this encoder, okay, directly we will get the if it is Hall sensor, we'll get the Hall ABC, or if it is encoder, we'll get the ABC and index pulse. Okay, and if and inside this encoder port, right, the user can directly mention the PPR of the encoder. Okay, so right now, as of now, we are getting a PPR of 2500 PPR of encoder. If we directly mention the PPR of the encoder, we will get the speed of output. Okay, so this speed output I can directly use in my control logic. means user no need to implement additional control logic to get the speed from the encoder pulses. Okay, that can be easily done. Okay, now I move on to the control systems inside. Okay, so this is the heart of my control logics. Okay, so here what we are doing it over here. Let me zoom it in these portions. Let me zoom it to this portion. Okay, in this portion I am measuring all the three currents. Okay, then from the three currents I'm converting, I'm doing a Clark transformation from converting ABC signals to DQ transformations. Okay, and the theta, right, from the encoder we are getting the electrical theta. Okay, that theta again we are converting to mechanical theta. Okay, and from there we are getting the sine signal, sine ABC signal, sine and cos signals. Those same signals I'm using for Clark and Park transformation, and here inverse Clark and Park transformations. Now at the end of IA, IV, IC, I am getting the IT and IQ component. Okay, so generally this IQ component we are using for controlling the speed of the motor. Okay, so for controlling the speed of the motor we are using a speed loop over here. So user can use directly MATLAB PI block sets also, or MATLAB Clark and Park transformation block set also here. Okay, so what about the okay? So this reference speed we are providing by using one ramp signals, because we don't want to give the sudden speed of the motor. So that's why we are implementing one ramp signal. Once this user is entering the speed, this speed is come over here and it will check with the actual speed. Okay, based on that it will generate the IQ reference. Okay, this IQ reference is going to compare with the actual IQ of the motor. Okay, and based on that it will generate the VQ reference. Okay, that VQ reference is coming to again our VD and VQ loop. Okay, so from VD and VQ loop we are getting the D and Q component over here. Okay. Now this D and Q component we are using again the inverse transformation over here. So as I told you, we are doing our mathematical implementation of inverse Clark and Park transformation. The user can use the MATLAB blocks also to do all those things. Okay. So at the end we are getting all those signals. Okay, we are getting sine A, sine B, and sine C. All three signals. Okay, those three signals I'm giving back to our controller. Okay. So from the controller, by using these PWM block sets, I am generating the pulses. Okay, because I have to mention to our controller, like from this particular hardware code I want to generate the PWM pulses for this control logic executions. Yeah, so inside the PWM log, right, I can mention the PWM port number. Okay, from which port I want to get the actual PWM output. Okay, and what type of carrier signals I want, that also I can select. I can select the triangular signals, I can select the ramp signals. Okay, inverse triangular. Okay, based on applications. And if you are working on multi-level applications, you can give different multi phase shifted PWM pulses or carrier signals also. Those I can give you. Okay, now come to frequency. So whenever we are running any converters, right? So user can give a fixed frequency for running that particular system. A user can make a variable frequency also. If I'm making it as a variable, so that means user can vary the switching frequency while running the actual hardware or actual plant. Okay. Then as well as along with that, we are providing page control options also, because in some of the applications, right? Let's say DAB applications, right? There are some IntelliB applications. There user want fixed phase shifted carrier signals. Okay, or some applications you require variable phase shifted carrier signals. Okay, directly by enabling this, user can directly enter the angle, phase angle difference. Okay, once click on this, user will get that particular carrier signals. Okay, and top of that we are providing options to give a rising edge and falling edge delay for the dead band. Okay, between high and low pulse. In the low pulse also, if user is running any converter, we can give complement of the top pulses. Okay, or else user can independently create also carrier signal, because those PWMs are independent, user can make it. Okay? That's not a problem. Once we make on this, we are getting the PWM pulses from PWM1 to PWM34 and PWM56. Okay, now those signals those signals I'm introducing over here. And what about the signals I want to see it in real time? Either it is Hall signals or internal D or Q component, the ID and IQ component, then the ID and IQ reference generating from the PI loops, Okay, then all the voltage and current loops. Okay, everything I want to see it in real time. That's why I applied a probe over here. Okay, and we are using this web development block sets. Okay, so inside this block set, user can give the sample time of the control logic. Means 10, if I the lowest sample time, it can go up to 10 microsecond. Okay, if I mention the 10 microsecond, my entire control logic is going to run on the 10 microsecond. Okay, and here we are providing the buttons, okay, to generate the auto code. Okay, directly if I click on generate model, okay, it will generate the executable C code for me. And if you directly click on the build model, okay, it will generate the binary file for me. Let's say let me and for the controller configuration, right? Let's say let me click on the build model. Okay, once I click on the build model, you can see the compilation is started. And if it is a MATLAB command prompt, okay, so inside this command window, the build process is going to start, okay, and it will take a couple of seconds to generate from your executable model to implementable code. Yeah, now my code is generated. You can see by click on this, my code is generated. Okay, so once the code is generated, now MATLAB is independent. Okay, I can close the MATLAB also. Now MATLAB is no use. Okay. So once MATLAB is no use, now I will move on to our software. Okay, okay. So before moving on to the softwares, let me show you the real hardware interface. So this
Yeah, we
is
are
the
able to see.
real-time controller we are talking about. It's a RCP platform. Okay. So let me zoom on to this PWM iOS ports. Okay. So those are the iOS ports are available over here. Okay. These ports are customizable. Okay. So depending on the user requirement, we can customize the number of iOS. Okay, so it's a ready to use PWM ports. This PWM ports, I'm using one connector to interface between the controller to converter. Directly one-to-one connections I'm making by using these cables to run the converters. Now come to other IOs. So those are the digital inputs and digital output pins. Okay, and those are the encoder interface I'm making it from our actual motor to controller. Okay, and the other IOs are available. You can see it over here. So a couple of communications protocols. Let me make the camera stable. Couple of communication protocols like CAN communication protocols are here. RS-232 and RS-485 protocols are here. Okay. Then the relay channel also providing for safety and protection is perspective. Okay. Then analog output, and top you can see the analog input channels are there, and this input channel is also customizable. Okay. As of now, it's contain 8 number of analog input. The analog inputs are plus minus 10 volt. Okay, and the back side of the controller, you can see all the embedded voltage and current sensors. Okay, so those are the current sensors and those are the voltage sensors. Okay, now let me show you the overall hardware connection, how we are making it. Let's make it this. Yeah, so this is the converter, IGBT based converter module I am using. Okay, it contains diode bridge rectifier module as well as the inverter. Okay, so this is the architecture of the converters. Okay, so at the input, I'm connecting the single phase input over here for the diode bridge rectifier module, and it is giving me the DC. So this DC, DC I'm converting into AC signals. Okay, this 3 line you can see it RYB. That 3 lines is coming to the current sensor for current measurement of the motors by making the series connection to the motor. Okay, and for measuring the voltage, I'm using some jumper over for measuring line to line voltage of the motor. Okay, and this is my motor. So this is my PMSM motor. Okay, and the back side of the controller, the PMSM motor is giving the encoder and Hall sensor modules. These signals I'm interfacing with the controller. So this is overall controller and the hardware's connections we made. Okay, and by using this Ethernet communications protocols, this Ethernet cable I am connecting to my PC. So this Ethernet cable directly I am connecting to my PC. Okay, and by establishing the connections, I'm going to execute the controller. Yeah. So now I'll move on to the hardware execution. present my screen. My screen is visible, right, sir?
Yes, yes, it is. Your screen is visible.
Now this is the software we are using for interfacing our control logic, okay, to the real hardware. Okay. Now inside in these softwares, whatever the code, executable code generated right from the control logic, that will generate in the term in the form of bin file, .bin file. That bin file we are going to load it to the controller and click on launch model. So once you click on the launch model, we'll get a interface like this. Okay, so these dashboards are fully customizable. Okay, so based on user, initially user will get an empty dashboard like this. Okay, so user can customize the dashboard according to their requirements. Okay, and all the input parameters will come to input sections. Those are the input parameters. I made it as a variable because I want to change those parameters in real time. Okay, and in the probe I can see all the current voltage plus all the loops outputs. Okay, id, iq, reference, actual current, all signals, voltage sensors, reference speed, everything I can visualize over here. Okay, now let me click on the run options. Now it is not running. Okay, here you can see it is not running. Now if I click on the run options, okay, the controller will give you the beep sound and it will load it to the controller. Okay, and here in the run time, right, you can see it in the run time. You
ಇದೇನು
can see
ಬರ್ತಾ
it,
ಇದೆ
this is running in real
ಸ್ಕ್ರೀನ್
time.
ಅಲ್ಲಿ ಏನು ಬರ್ತಾ ಇದೆ ಸ್ಕ್ರೀನ್ ಅಲ್ಲಿ ಏನು ಕಾಣ್ತಾ ಇದೆ I'm sorry please go ahead.
Yes. So here my control module is running in real time. Okay, and based on our requirement I have given the input parameters. Okay, so all the input parameter directly user can enter the value. Okay, or else if user wants to give it in format, simply nothing, drag and drop to any empty places like this. Okay, so drag and drop to empty places like this, user will get options, text, fill, slider, like the options. So we are using this to make a dashboard. Okay, now for any signals to view, we are going to probe section. Those are the signals, real-time signals are coming from the controller. I can right click on the control dashboard. I will get a time plot, general plot, 50 panel, power panel, power analyzer. Like that way I'll get all the options. Okay, let me take a time plot. I'll take a time plot. Let me drag and drop any signals to here. So I can see the signals that are coming from the hardware in real time. Okay, like that way I can do all the signal analysis. Okay, now this is the customized dashboard. I make it from here. So the DC voltage for the motor I've given 320. Okay, now I'm going to execute the loop. First I'll turn on the loop and I'll give the duty, topical duty to run the motor. Now you can see once I increasing or decreasing the topical duty, based on that I am getting the speed of the motor. Okay, and this is the voltage waveforms of the motor, input voltage, line to line voltage, and this is the current of the motor. Okay, and if you see in the form of RMS voltage, so what you can do, let me go to a empty dashboard. Let's say I want to see this current, RMS current, right? I can simply drag and drop this signal to any places. Then I can see the RMS value, average value, maximum value, minimum value, right? Let me click on the RMS value. Then I can select the defined formats. Let me take a text field, so it will show you now the RMS value is 0.28 amps of current. Similarly, for voltage also, you can also drag and drop. Similarly, drag and drop the line voltage over here, choose the RMS and see the meter text. Now voltage is coming 0.53 and the current is coming this. Okay. Now this is I am running it in real time. And if you want to see the all position, all signals, right? So this is my Hall signals over here. A, B, and C Hall signals are coming. Okay. Based on these Hall signals, I am generating the theta, stator theta. Okay, those theta I am using for Clark and path transformers. Yeah. Now this is tropical method, right? Like two-phase excitation. Because of that only the current waveforms and voltage waveforms you can see it is distorted, right? Now I will turn off the tropical, right, and I'll directly move on to the FOC. FOC enable. So inside this FOC enable, once I click on the FOC enable, based on the reference speed, okay, it is going to run my motor. Okay. Yeah. So now let me increase the speed of the motor. Now I am entering the input speed of 500 RPM. Okay, so based on the 500 RPM, you can see my motor current also increased. Now that's the motor voltage waveform, and this is the pulse sensor concatenator. Okay, let me run the motor at let's say 1500 RPM. Simply click on enter. Let me click on enter, and you can see whatever the reference speed I am entered, the motor is following the reference speed. Okay, it is drawing that much amount of current. Now, how will validate whatever the loops or control loops we have implemented, right? The loops are going properly. You can see all the individual signals like ID, IQ signals. Okay, okay. So this is my D component of current. Or this is my Q component of current. Similarly, if you want to see the reference of D current, right? Those signals also you can simply drag and drop. Let's say, see the error. This is the D reference. Okay. So D component of current, Q component of current. Then okay, so this is the ID and IQ component, IQ reference signals. Okay. Let me drag and drop the IQ reference signals and let's say change to red. Okay. Now you can see it over here. Now, okay, let me change the speed. Okay, while running the Q loop. Okay, this is the speed of the motor, right? Let me give let's say 300 RPM. If I click on this, yeah. So this is my reference and actual current. Okay, based on my control logic. So by seeing those parameters, you can tune all those loops. Let me give a different speed of my motor. Let me give let's say 2000 RPM, or if you want to rotate my machine in reverse directions also, right? Those things you can do. So like that way, based on your input parameters changes, right? You can see all the output parameters, all the loop parameters. Okay, everything you can visualize it over here. Now, if anything, let's say some loop is going out of control, so directly by using this input parameter, you can tune it. Or if you want to, let's say, go back to your MATLAB model, right? And wants to modify your control logic. Okay, what you can do, you can directly move on to your MATLAB model, do the modification, generate the code again, and come back to the control loops. Okay, so this dashboard, once you prepare it, this dashboard is going to save it to your save it in some folder. Okay, and once you regenerate the binary file, that by implementing or by modifying the control logic. Okay, though again no user no need to create the dashboard again. Okay, because once you create a dashboard, right, for a particular control logic, then if you are running the same logic by modification of the control logic, right, it's like a one-time effort. User have to create a dashboard for one time only. Okay, and then small modification user can do it, not a problem. User no need to worry about, let's say, if user generated the binary code again, right? So user no need to worry about to come back to model again, generate the dashboard to run that particular application. User no need to worry about it. It is like auto load options will be there. Directly it will automatically detect the dashboard and it will load your updated code. Similarly, let's say I want to run my motor at the negative speed. I can directly enter the negative speed reference. Okay, so based on the negative speed reference, so first motor will stop, then again it will start in the rotate in the negative direction. Then 500. Yeah. Now my motor is rotating on the negative direction, and then how we are estimating the motor power? How we are calculating the motor power, right? So we are using our power panel. Inside this power panel, we are selecting the line voltage and line current we are measuring from the motor, and those line voltage and line current I am selecting from the sensors. Let's say voltage A, voltage B, and voltage C. Okay. By using this, I am making the power. Let's say I turn off the control logic. Now everything is in ideal conditions. So this is about hardware, sir. If anyone having any queries regarding this, right? Yeah.
So I was basically asking whether this particular uh, uh, real-time machine that you have is it
Yes.
tailored for power electronics applications, or I mean, is it also in some sense customizable for other applications that people may be working on? For example, I'm interested in drones and aerospace kind of applications.
Yes. Yeah.
Will it be possible to use this for hardware in the loop or rapid control prototyping for those domains as well?
Yes, definitely, sir. This controller is definitely customizable for those applications also. So as of now, what we are doing, so the control logic development, right? We are using MATLAB Simulink workflow, standard workflow we are using, right? Uh, Inside MATLAB block set, inside MATLAB, if you are using, let's say, some drone control block sets also by using control libraries, what is providing by MATLAB, right? If those block sets are able to generate the compatible C code, okay, this controller is capable, sir. Okay. And so that for rapid control prototyping, okay. And if you want to go for hardware in loop system, right, we are having one more product that is specifically meant for hardware in loop system. They are also the same thing, okay. We are dedicating
So we need
to
two different systems for RCP and HIL, is it?
Generally, yes, because the RCP systems will always come with embedded all sensors. Because when it comes to hardware testing, right, you no need to worry about the hardware integration issue, IO integration issue. You no need to worry about PWM integration issue. You want a small RCP product that will help you to interface with your hardware directly and run your control logics in your RCP box and validate your control logics, right? When it comes to RCP or HIL systems, right? In HIL system, you have to bring your own sensors, then interfacing you have to do, gain modifications you have to do, okay? Then you have to connect hardwares, then you have to test. So you don't know which sensor may got give any unexpected result. Okay, those constant will come when it comes to you want to test hardware with HIL systems. Definitely, that approach also you can do, but that is not preferable for when it comes to industrial testing, sir.
Okay.
We require one
So again, I mean, I'm sort of just getting introduced to all of these things. So I apologize if some of my questions are a little naive. So I mean, I was just sort of reading up on another sort of a similar system. I'm sure you might know about it, which is SpeedGoat. So is your product sort of comparable to SpeedGoat, or is it a competitor? How does it compare?
Speed
So,
boat.
So that's a live concept. So yeah, good morning, sir. So I am Pranay, working as senior sales manager. So yeah, I understand your query. So this that as a technology domain, we are into similar space. Yeah, but we being in indigenous, we are able to customize it depending on application requirements to the clients. And see, both of us we operate in the same domain of rapid control prototyping and HL kind of HL solutions. Whereas we have got some flexibility with respect to that because this is our own product which we are developing indigenously in it. And then coming on to your question with respect to RCP plus HL, do you have separate product? We are working on a single unified platform where you can do real-time simulation and RCP as well. Yeah, so that can be a mix of both basically.
Okay. So yeah, my question was more on the technical side. I mean, so is there? I mean, technically, regarding the technical specifications and so on.
Yeah.
I mean, do you sort of see any sort of an advantage for use that your product, allows with respect to speed quote or vice versa?
So see that exactly depends on what application you would like to use, because as you are telling that you want to use it for aerospace applications or a drone applications or something. Majorly, see the internal architecture of all these things are your motor controls, basically either on FPGA or using a processor. Yeah. So the advantage what we have is that we can customize the controller to meet the client requirement. Let us say most of our controller, whatever we have seen till now, is completely scalable and it can be customized. Yeah. So tomorrow, like with whereas other products, whatever we have come to the best of our knowledge is that so they have fixed IOs and fixed thing. Whereas in case let us say you are working on aerospace application where you require higher sampling rates and higher frequencies or running on FPGA, we have got a core expertise of doing that as well, which can be customized to meet your requirement. But others one, I don't think so. We have that option currently. That's what to the best of my knowledge. You can correct me in case if I'm wrong. Yeah.
Yeah,
So that
so again, I'm very very new to this, so I really sort of apologize if some of my questions are not sort of make sense. So with NIPX, I also that was one of the other products that I was currently looking at.
yes,
Uh,
sir.
but they do advertise themselves as saying that they have customizable IO modules and so on. It can be expanded in the future and so on. So is that right or?
Yeah, see, basically they work on a chassis kind of thing. Okay, you just scale up the chassis as per your requirement. But I think today, I think they are not dealing it directly in the market. They are working with majority of the resellers or channel partners. So whereas we work with the customers directly to understand the application and we are able to customize it thoroughly. So we have that option as well. The whatever you said is right, but the catch is that the support point of view, because see whatever we feedback, let us say in IIT Madras only, as you are telling that you are from IIT Madras, so there are some faculty who are using my systems. Basically there are three controllers sitting there who are using my system for last 4 5 years basically. Yeah.
Okay.
So there have been some clients who have used NI systems and then switched over to my systems as well. Yeah, because of the advantage with respect to ease of use and then support, and then we are available there because we are the core, we are in the customization. These three are the main reasons they switched over to our product actually.
Okay, got it.
Yeah,
And would you mind giving me the reference of the people in IIT Madras who are using the product?
yeah. You can speak to Dr. Deepak Ronanki there. Yeah, and then
Deepak Ronaki. Okay.
yes, Dr. Deepak Ronanki, you can speak to him, and then you can speak to Dr. Srikantan sir as well. Yeah,
Just
yeah.
give me a minute.
Srikantan from Design Engineering Department. Yeah.
Uh, Deepak Ronaki is from which department?
They're both are from Design Engineering Department, sir, but they work majorly in the area of motor controls and power electronics, CVs and stuff. Yeah.
Okay. And you also mentioned a third person, right?
Dr. Srikantan, sir.
Srikantan, Deepak Ronaki.
Dr. Srikantan and Deepak Ronanki both are from Design Engineering Department.
Okay.
And
Anybody else?
in electrical department also we are given to Dr. Sriram Srinivas sir, but as of now I don't think so they are using it actively. Yeah.
Okay.
But if
Okay.
you want a feedback, because Srikantan sir and Deepak sir team is using exclusively our products for a long time. So you can,
Okay.
they have already published some international journals and international papers as well using the product. You can get a feedback from them as well. So, and we have given the most of IITs and IITs, other IITs and IITs are also our clients. Yeah, they're all using our
Okay.
system, IIT Bombay, IIT Kharagpur, IIT Madras, IIT Kanpur, everyone are using our systems. So you can take a feedback from
Okay.
them as well. Yeah.
Good. Sounds good. Yeah. Thank you.
We will.
Thanks for the time. Yeah.